In this video, I would like to talk about Euler's formula and two of its amazing applications. We will first prove Euler's formula, then we will use it to derive a formula for the tangents of a triple angle, and then we will prove that in a triangle, the sum of the tangents of the angles is equal to their product. Then I will mention some other cool things that can be proved using Euler's formula. First, recall that I is the imaginary unit, and it is equal to the square root of -1. Raising I to the 0th power, we get I to the 0 is equal to 1. As we multiply both sides by I, we get I to the first power is I squared is -1, I cubed is I to the 4th is again 1. And now we see that as we raise I to higher powers, the numbers on the right will begin to cycle. It's important to note that I to the even power is always real, and I to the odd power is always imaginary. We will now use calculus to prove Euler's formula. If you don't know calculus, you can skip this part. Recall the Taylor series expansion for sine x in red, cosine x in blue, and e to the x in black. Through a stroke of ingenuity, we replace x with I theta. Notice that as we simplify the infinite series, we get an alternating series of real and imaginary terms. If we group the real and imaginary terms, we get the desired result. Now, recall the trigonometric ratios. Sine of theta is opposite over hypotenuse, cosine of theta is adjacent over hypotenuse, and tangent of theta is opposite over adjacent. If we choose a point A plus IB in the complex plane, here the vertical axis is the imaginary axis and the horizontal axis is the real axis. By using trigonometric ratios, we can see that the x-coordinate of A plus IB is r cosine theta, and the y-coordinate is r sine theta. The angle that the vector A plus IB makes with the x-axis is called its argument. From the diagram, it is clear that A is equal to r cosine theta and B is equal to r sine theta. Let's write it down. Now factor out r, and now use Euler's formula. This means that any complex number A plus IB can be written in this form, which is called the polar form. Let's write two complex numbers u and v in polar form. And let's use laws of exponents to multiply them. Right away, we arrive at an important observation. The argument of a product of two complex numbers is equal to the sum of their arguments. In other words, when you multiply two complex numbers, the angle or the argument of the product is equal to the sum of the angles or arguments of the two original numbers. We will use this observation to find the formula for tangent of 3 theta. Consider the below diagram. Using trigonometric ratios, it is clear that tangent of theta is equal to t over 1, which is just t. This is an important observation. We will use the same trick in the next problem. If we cube 1 plus it, the new argument will be 3 times the original argument, or 3 theta. Quickly recall the formula for the cube of a sum. If we expand 1 plus it cubed using this formula, we get 1 plus 3it minus 3t squared minus it cubed. From the diagram, it is clear that tangent of 3 theta is opposite over adjacent or imaginary part of 1 plus it cubed divided by the real part of 1 plus it cubed. Substituting, we get 3t minus t cubed divided by 1 minus 3t squared. Recall that t was tangent of theta. So substituting, we get the formula for the tangent of the triple angle. Now let's prove that the sum of the tangents of the angles in a triangle is equal to their product. In this diagram, angle C is more than 90 degrees, so its tangent is negative. The derivation is similar for the case when tangent of C is positive. We first use the same trick as in the previous problem, defining u, v, and w as in the diagram. Note that argument of u is equal to angle B, argument of v is equal to angle A, and argument of w is equal to angle C minus 180 degrees. If tangent of C was positive, then the argument of w would just be angle C. Let's remind ourselves that the argument of the product is the sum of the arguments, which must be either 0 in this case or pi in the case when tangent of C is positive. Recall that pi radians is equivalent to 180 degrees. Substituting in the values of u, v, and w, we get this long expression equal to 0. Now, what is the imaginary part of this product? When we expand it, we get an imaginary number by using one of the imaginary terms in the product or by using all three. If we use just one, we can get an imaginary term by using I tan A times 1 times 1, or 1 times I tan B times 1, or 1 times I tan C. If we use all three terms, we get I tan A times I tan B times I tan C. Thus, the imaginary part of this product is going to be equal to tan A plus tan B plus tan C minus tan A, tan B, tan C. Recall that I to the third power is negative I. Bringing tan A, tan B, tan C to the other side yields the desired result. Now, what about other applications? Well, for example, you can find a closed formula for cosine theta plus cosine 3 theta plus all the way to cosine of 2n minus 1 theta. Or you can prove this obscure statement about alternating sum of binomial coefficients. Or you can solve this 6-degree polynomial. Or you can prove that if we erect similar triangles on the sides of any triangle, then the triangle formed by the 3 in U vertices has the same centroid as the original triangle, as in the diagram. I hope this little presentation will inspire you to look deeper into Euler's formula and into complex numbers in general. If you are interested in complex numbers, I recommend Tristan Needham's book, Visual Complex Analysis. Thank you very much for your attention.